Quotient rings and homomorphisms. So in this lecture we will be essentially repeating same theorems, same results, same definitions, the same ones as we have learned when we talked about quotient groups and homomorphism. So you remember that when we formed a quotient group out of group G, we have taken a normal subgroup, and then G over N, we formed a quotient group. Remember that? And then we studied the relation of homomorphisms with this quotient group. We will be doing the very same thing today, but with quotient rings. Quotient ring is essentially the same as the quotient group, but as you know, group has one operation only. The ring will have two operations. So quotient ring is a quotient group with addition operation and also with a multiplication operation. So what we will see today is a repetition of the results of quotient groups, but we will extend that to take two more operations instead of one. And you know the operation inside quotient group was on the cossets of the normal subgroup N. But now the quotient ring will be the quotient of a ring over an ideal, and we have mentioned that in our last lecture. So we will have cossets of the ideals, and then we will define addition and multiplication and show these definitions are well defined, and then we form the quotient ring. Okay, so we start with the following. Okay, so my computer is a little slow for now. Okay, so we will deal with the set of congruence classes modulo an ideal. This set makes itself, it is a ring which we call quotient ring. Okay, so we start this way. Let I be an ideal in a ring R, and take the elements of the set R over I to be the whole cossets of I, where A here can be any element from the ring R. Now I go back to what I wanted to write. The quotient ring R over I will consist at the end of the cossets of the ideal I, where A is any element in the ring. And you have seen that many elements will give the same cosset, and we will say two elements are congruent modulo an ideal. We defined that already. When two elements are congruent modulo an ideal, then they give the same cosset of the ideal I. Okay, so this is the quotient ring, and we will prove it is a ring. But you know a ring is associated with two binary operations, so we will define the addition and multiplication of cossets as we see in the following theorem. Okay, but in here, in this theorem, we define the addition and multiplication, and actually we already defined this addition and multiplication in the last lecture. But today in this theorem we will show that this addition and multiplication are well defined, which means this operation do not depend on the representative of the cossets. Okay, so what does that mean? Let's see. So choose an ideal I in R. Then if A plus I equals B plus I, that means if A and B gives the same cosset as I, that means A and B are congruent modulo I. Okay, and also C and D are congruent modulo I. So essentially here we are saying that we have the same cosset. It is sometimes denoted B plus I or A plus I. So we have the same coset, but one time it is represented by A and another time it is represented by B. Same thing happen here. We have the same coset, but sometimes it's represented by C and some other time it is represented by D. Now what does this theorem says? So these are elements in R of A. Now this theorem says if I choose the representative A for this coset and representative C for this coset, and if I multiply or add, I will get the same results if I use the representative B for the first coset and D for the other coset, multiply and add, and I still get the same result. So in here we say A plus C is the same as B plus D, modulo I. AC is the same as BD, modulo I. Okay? And even if we go and say, okay, we multiply A times D, it will be the same as C times D. They are just representative. We can interchange the rules of C and D or B and A, no problem. Okay, now if you want to rephrase this theorem in your own words, you may say that if A and B are congruent modulo I, and also A and C and D are congruent modulo I, then A plus C is congruent to B plus D. And also A times C is congruent to B times D, modulo I. Good. Now, I want to emphasize thing here before we prove this thing here. I want to emphasize that if you notice here, the addition, so let me go back and write something. When we write A plus I, now this becomes for us as a notation. This is an object. So the plus in here is not now considered as a binary operation here. Okay? We know that it is A plus a small I for I, small I belongs to the ideal. And now the plus here comes from the ring R, because each of A and I are elements from the ring. So when we add them, we are using the addition of the ring, okay? But now in this addition and this expression will become a symbol, a notation, an object for us, okay? So this addition now has no meaning as a binary operation here. It depends on that. Now why I am saying that? It is the addition I talked here about is the same as these ones. So now these are additions to get the coset. So these are samples. Okay. Now if you notice here, what we are doing, A plus C is the addition from inside the ring R. B plus D is the addition from inside the ring R. Okay. And this addition is the same one as we talked about. And if we go back a little like this, if I say if I take this coset and then say I want to add it to another coset, C plus I, okay, and we know the operation we have defined already is A plus C, so we add the representatives, okay, and we add this inside R. Now what I want to say here, okay, now as we have talked above, this addition here is an object for us now. It is just to denote a coset, okay, but now I want you to notice something. This addition in here, as we said, is the addition of the ring R, because A and C are elements of R. But now this addition in here is what we are defining as additions for the quotient ring that we will produce. So this addition here is defining the new operation that we will use to add cosets. I will repeat the same thing here for the multiplication. So we will say a plus I, if we multiply it with c plus I, then we multiply a times c, and then we take the resulting element and make a coset of it. Now we go back. This multiplication here is inside the ring R, so it is the multiplication of the ring R. But this multiplication here is the one we are defining for the quotient ring. And again, the addition here are just to produce the coset. So this is very detailed for you just to have a feel for these operations. Okay, now this operation in here, this theorem in here says that the operation is well defined. Okay, so this will be mentioned below there. But now let's go back and prove this theorem. And actually, if you look at the book, it says it is an imitation, mimicking for the same proofs of the theorems that we have seen in chapter 3, where we studied quotient rings, and they are truly the same. What I will do, we have done this before when we worked with normal subgroup, so I will let you, and you must go and prove it. So I will say this is number 1. So I will leave it for you to prove number 1. We need to prove number 2. We want to prove this from here to here. And I will leave that number 1 to you. Okay, so to prove number 2, we want to show that AC, the coset of AC, is the same as the coset of PC. So let me write that in green. Want to show AC. Okay, so I shall not write the parentheses, and you know that this is AC, then we take the coset. We want to show it is the same as BD plus I. Okay, but what does that means? That means we want to show, remember a theorem, and let me write that theorem in here, and let me use different notations. We say x plus y, the coset of x plus the coset of I represented by x is the same as the coset of I represented by y, and this is true if and only if what? X minus y belongs to I. You remember that? Okay. So we want to show AC gives the same coset as BD. That means we want to show that AC minus BD belongs to I. Okay? So how we do it? And we need to use the informations here. Let me clean all these things. So how we reach what we are going to prove in red, the last line in red. So let's play a little with the hypothesis. First thing, we need to remember that I is an ideal. Okay, the computer is giving me some hard time. My computer is going not responding properly, it's going a little slow, so let me see. Okay, so remember we have an ideal, and remember that this says A minus B belongs to I, correct, by this theorem here. And this says C minus D belongs to I. Good. And we want to use that I is an ideal, and we need all that to prove this thing. Okay, let's see. We will write this expression AC minus BD as AC minus Okay, we will add something. Okay, so what is the trick in here? So what if we add AD and subtract AD? No. What if we add BC? And that will work. So let us add BC and subtract BC, so we change nothing. Minus BD. Okay, so I was thinking actually and looking at this because I want to benefit from that. Okay, so let's rewrite this. We will have this as what I will do. I will say I want to subtract and then add. So I will just go in here. I say it doesn't matter which one does not affect. So okay, I will subtract BC and then add it. Now we are in a ring, so we can use the distributive law in reverse. So we will have C as a common factor here, so it will be C times A minus B, and we will have B here, and this will be C minus D. Okay, and this shall belong to I. Why? Because A minus B belongs to I, and so okay, so A minus B belongs to I, and I is an ideal. So if we multiply any element from the ideal I and any element from the ring, the result of the multiplication must be absorbed inside the ideal I. And now C is any element from the ideal, so any element from the ring, and we have A minus B belongs to I, so C times A minus B must belong to I. And also same thing, C minus D belongs to I, and so B times C minus D belongs to I for the same reason. And now we have these two terms belong to I, and therefore their addition must belong to I because I is an ideal. Therefore we have C times A minus B plus B times C minus D must belong to I, and then we are done. Okay, and so we proved what we wanted in green. So great. Now what does theorem 6.8 tells us here? That we have defined already addition and multiplication in R over I, and remember this is what we have defined. This is the addition of the quotient ring R over I. Okay, and this addition here is between elements in the ring R. Okay, and the other addition notation that left in black are now just symbols to produce the cossets. And same thing for multiplication here. The multiplication which was defined here is the one for R over I, while the multiplication in here, there's no space, is the one of R. Okay, so what we have shown that theorem 6.8 tells us that addition, the cosset addition, is independent of representative choosing. The cosset addition and multiplication, I shall write here, and multiplication. Independent, this is what we want, independent from the representative chosen. That means these operations, so I will write them this way, these operations will defined. That's what we mean by well defined. Okay, so when you see a well defined expression for an operation, that means the object that you are operating might be represented differently by different elements. So it does not matter which representative we use for that operation, the resulting object will be always the same, no matter what representative comes out for that object. Okay, and we will see in a while, we will worry about a well-defined function. What we are talking here is well-defined operation, and the well-defined function you worry about it when the domain of the function consists of equivalence classes or of cossets, where they are represented by elements. So a cosset might be represented by so many and might be infinitely many elements, and you don't want that to affect the image of that element under the function. So no matter what element you use inside that function, the result will be always the same. That will be called well-defined function, and we will see it in a while. Okay, now we have well-defined operations, and we have seen actually before such examples. This is the ideal generated by 3 in Z, which is the same as 3Z, and now this becomes Z over 3Z, and you know this is isomorphic to Z3. Okay, and now we have the cossets here to be let me write that the cossets are 0 plus 3Z and 1 plus 3Z and 2 plus 3Z. Okay, now if we what if we want to multiply 2 plus 3Z? We learned about how to do addition. What if we want to multiply them? What we get? So we get 2 times 2, which is 4. This is 2 times 2, and then take it and make the cosset of it. So we have this, but we don't see 4 as a representative in here, so we know this is the same as 1 plus 3Z. Okay, now inside Z over 8Z, for instance, which you know it is isomorphic to Z8, you know how to do addition of cossets, but now let us choose 2 cossets and multiply them. What if we multiply 3 plus 8Z times 5 plus 8Z? What we get 3 times 5, which is 15, plus 8Z, but we know 15 modulo 8Z, modulo 8 is 7. Okay, so this is examples of multiplication of cossets. Okay, another example, we have worked with this ideal in the polynomial ring whose coefficients are from Z. So we have taken all polynomials whose coefficients are Z, and we have taken a substitute from there, which is all polynomials that has no constant term, or I say sorry, not the zero constant term, all polynomials that have even constant term. And we have proved this is an ideal, and actually we have proved these are the 2 cossets of it before. So the factor ring Z of x over I will consist only of these 2 cossets. Okay, good. Now I kept saying a factor ring again and again, but we did not prove it is a ring so far, and now we will prove it in this theorem. Let I be an ideal, and in a ring R, then part 1 says R over I is a ring with addition and multiplication as we have defined already. If R is commutative, then the quotient ring R over I is commutative. If R has an identity, then does R of I will have an identity. And keep saying R of I is a quotient ring, and here it is, or factor ring of R by I. Actually, why we call it quotient? Looks like I is dividing R, and this is correct, and this is the idea. If we have R in here and choose an I, and we can just assume, oh, it is we can assume it is this area of the ring. Now make a cassette, choose any element in the ring, you say R, and make a cassette, and you will get another cassette. For sure, R here is not from I, because if it is from I, then R plus I is the same as 0 plus I, which is I itself. Now use another element which is not in I or not in R plus I. Say it is A, and then take the cassette. Now choose B, which is not in any of these cassettes, and then make another cassette, and so on. Now, why did I say choose B, which is not in any of these cassettes? Because if you take B in one of these cassettes and then make a cassette of that B, then it will be the same as the cassette you have taken B from. Okay? Like I'm saying here, for instance, if you take B from A plus I, that will give the cassette formed by B is the same as the cassette formed by I. And conversely. Okay. And keep doing this. The cassette might be finite or infinite. And now this why literally we mean factoring. R is factored or by I, or it is a quotient ring of R bar I. Okay, now we need to prove R of I is a ring indeed. So to prove one, recall we learned actually before previously we learned that R over I, now with the addition of R over I give it this notation, is an abelian group. It is a group. It is de facto group, you know, right? Because I is an ideal of R. R is a ring. So R is an abelian group. And I is a subgroup of R. So it is a normal subgroup, because we are in a abelian group. So I is a normal subgroup of R, which is a group also. So R over I is a quotient group with the addition of cassette. So we are done with that. And to prove R over I is a ring, we need to prove it is an abelian group. And then we are done with that. And then we prove 3 more axioms. The associativity in multiplication, and distributivity, multiplication over addition, and also closed under multiplication, right? If we prove these 3 axioms, then we got R, then we get R over I is a ring. So let's prove R over I first is closed under multiplication. And we know here we mean cassette multiplication. Okay? But this is so direct. Like, we know it's A plus I times B plus I. It is AB plus I. And that definitely belongs to R over I. Why? Because AB is from inside the ring R. Because the ring R is a ring, and AB R is a ring, so, and it is closed under multiplication. Each of AB comes from R. Okay, so that was direct. we want to prove now associativity in R over I, associativity of multiplication. So let us see if we want to multiply A plus I, multiply it with B plus I, let's say B is in here, B plus I, which is multiplied by C plus I, and see what we get. Now this in here, multiply it, we get BC plus I, correct? Multiplied by A plus I, so this is the same as that. And now this gives, use the definition of multiplication of cosets, that gives A times BC plus I. Okay, now in here we will use the associativity of this multiplication in here, because A, B, C are elements from the ring R. So the associativity must hold there. So we will say this is AB times C plus I. Then we go back now and write this as multiplication of cosets. So it is AP plus I times C plus I. But this is the same as A plus I times B plus I, and then all of that times C plus I, and then associativity done. So we started with this and ended with that, and this gives the proof of associativity. Now what else we have? Distributive law. Distributivity in R over I. Okay, distributivity, and I will leave this for you to do it as exercise, and you must do it. Okay, so having all that will give us R over I is a ring. The set of cosets satisfy all the axioms of ring. Now what's left to prove in this theorem? Above there it says if R is commutative, then R over I is commutative. Is that correct? So I will play with the proof somewhere. Okay, so let me do it here. So just, it means A times A plus I times B plus I. We want to show it equals B plus I times A plus I. So we change the position of places of cosets. Can we do so? This equals that. Now, since we are assuming R is commutative, AB is the same as BA. So we will rewrite this coset, and this simply equals B plus I times A plus I, and then what we got, this equals that, and then R over I is commutative. Now, what is the identity, part 3 here? What is the identity of R over I? It says if R has an identity, then R over I has an identity. So if we say the identity of R is denoted by 1 sub R, then the identity of R over I, so I mean here, the identity of R over I must be a coset, right? A coset of I. Which coset? The coset which is represented by the identity of R. So this is the identity of R over I. This is the multiplicative identity of R over I. Multiplicative identity. And if we want to confirm it is a multiplicative identity indeed, we can play it with this space. Choose an arbitrary element in the quotient ring, which is a coset, multiply it by this element, a coset represented by the identity, and then simply it is A times the identity of R plus I, but this is simply A. Oh, okay. So we multiplied a plus I with 1 plus I and give us a plus I. Not changed. Okay, good. So we defined the factor ring R over I or quotient ring. Now we will define a kernel. We have seen such a definition when we worked with the group, and it is the same definition again for ring. So if we assume F from R to S be a ring homomorphism, and you know now a ring homomorphism preserves the two operations of ring, addition and multiplications. So the kernel of F are all the elements in the domain that goes to 0. So again, I would like to represent that. Assume this is a ring R and this is S, and F goes from R to S. So we will collect elements, maybe that goes to the 0 of S. So collect them all together and make a set out of them, and this will be called the kernel. And in fact, the kernel of a homomorphism is an ideal, and we will see that. Note that the 0 of the ring is in the kernel. Why? Because f of 0 equals 0. The image of the 0 of R is the 0 of S, and this is guaranteed by Theorem 3.10. Okay, and we have seen such examples before, taking f from z to z6 to take an integer to its equivalence classes. Then simply we know that kernel f, we denoted the kernel this way, consists of all multiples of 6, which is 6z. And for this example, theta is a function. This represents polynomials, right? So let me rewrite it here. Real numbers, polynomials over real numbers, which means all polynomials with real coefficients. And what we want to take a polynomial to some real number here that sends each polynomial in R of x to its constant term. This is a ring homomorphism, and I think we have seen it before. And let me rewrite that here. It might be interesting to see it this way. Theta takes polynomial, so the input of theta is polynomials, and the output is real numbers. Okay, so an element of the domain, polynomial. So I may represent it by b of x. So this is the input of theta. The input of theta. Okay, so what does theta do for a polynomial inside its parentheses? It gives you the constant term of that polynomial. But how you obtain the constant term of a polynomial? Substitute 0 inside x, right? Then you kill all the terms inside polynomial, but the constant term will survive. So simply take p of 0, and this will give the constant term. Okay, and this is a homomorphism. So I don't know if we proved it or no, but a ring homomorphism. So you need to prove the two operations, and I will leave it for you to do it. And now, what is the kernel of theta? That means, what are the polynomials that if we substitute 0 inside of them, then we get 0? And then you may answer, they are the polynomials that do not have constant term, or the constant term is 0. So let me write it here in words. Is the set of all polynomials in R of x that has or that have no constant term. So all the terms have powers of x. All terms have powers of x, and actually, according to what we have learned about principal ideals, that means the kernel is generated by x, right? Because any polynomial with no constant term, which means any polynomial that in each of its terms there is an x, you can take x as a common factor. Then it is x times some other polynomials. So what I want to say that any polynomial with no constant term is a multiple of x, right? And this is the principal ideal generated by x. So if I want to keep writing here, we mean by that x times j of x, where j of x is any element in the polynomial ring. Okay, so this is the kernel. Good. Now, a homomorphism is injective if and only if the kernel consists of the zero. We have seen if we have a homomorphism, then the kernel is not empty. It consists of the zero belongs to the kernel. Just we have mentioned it there. So the kernel is not empty. Okay. Now, if it happens that 0 is the only element in the kernel, then that means the homomorphism is one-to-one, is injective, and opposite. If the function is injective, the homomorphism is injective, the homomorphism not a function, then the kernel is 0, consists of 0 only, and we proved this in details when we worked with the groups. And there is nothing to add in here. Okay. Now, for example, this function that takes a real number and then gives you a matrix out of that real number. It takes a real number R and it forms a matrix using R this way. And this is a ring homomorphism. Have we proved it or no? And you prove it. We want to show it is on 2. Because what is the kernel of G? Kernel of G consists of all numbers, let me say R belongs to the real numbers, such that G of R equals 0. And the 0 in here is the 0 matrix, right? And how could this possible? What is R that produces such a thing? Nothing produces this except the 0 itself. Okay, and that gives G is injective. G is injective. Good. Now we learned about the kernel, and if you remember when we defined kernel when we were working with the groups, we proved that the kernel is a normal subgroup, and then we could factor the group over the kernel, and then we produced the first isomorphism theorem. And we will be doing the same thing now. Take a homomorphism from a ring to a ring, then the kernel of that homomorphism is an ideal, and so we can make a factoring over that kernel. So in here in blue it says every kernel is an ideal. Okay, every kernel is an ideal. So we will prove it. Let f from R to S be a ring homomorphism. Then the kernel of f is an ideal. Okay, prove it. We have proved kernel f is a sub-ring of R. Sorry, not yet. A subgroup I want to say here, because I already said that R is a group, and we when we worked with the groups, we proved it is a normal subgroup. And this is just simply by saying that AB belongs to the kernel of F, then A minus B belongs to the kernel of F. And you will, to prove that, use the homomorphism and distribute F over the negative. So what is left, so we proved this thing, and let me recall how to prove I is an ideal of a ring R. We will prove that for every A and B belongs to I, we assume I is a set, non-empty. Then if we prove A minus B belongs to I want to show that R times A belongs to I, right? For all A in the set I and for all elements in the ring R. This is what we want to prove. Correct? Okay. So let's do that. Let A be any element in the kernel of F. And let me complete the sentence. R be any arbitrary element in the ring R. Correct? Then F of A times R equals RA or AR, whatever, RA or AR. So we will stick to RA. So let me just let me stick to RA. We don't know. AR, RA might be different. Okay? So we will prove both of them. So what do I mean? Okay, let's see. This is a homomorphism. So it is R of A, F of R times F of A. But F of A is the zero of the ring S. Why? Because A belongs to the kernel. And that gives the zero. So we conclude that RA belongs to the kernel of F. Sorry, this is the kernel. Okay. Now we will show also that F of AR, okay, equals 0. So since F is a homomorphism, is a ring homomorphism, then we have that. So similarly, we have the same thing, and this is 0 in S, and we have A times R belong to the kernel of F. And then we are done. So kernel F is an ideal in R, and the ring R. Okay, good. So every kernel is an ideal. What about given an ideal? Can I make it or obtain it as a kernel of some homomorphism? The answer is yes, and we have done the same thing when we work with a group. If we obtain a normal subgroup, then we define the homomorphism whose kernel is that normal subgroup, and we will do the same thing here. Now we will start with an ideal I and in a ring R, okay, and define a map from R to R over I this way. So by, again, it's going from the ring R to the quotient ring, and it takes an element where to its coset, simply this way. Good? Okay. Now tell me here, we have seen, let me write it here, that the identity of the factor ring is the coset represented by the identity of the ring, assuming the ring has an identity. Now let me rewrite that. The identity of R over I is this coset represented by the identity of R, whenever R has an identity. Now, what if I ask in here, what is the zero of R over I? What is the coset that gives the zero? And you shall see this is directly 0 plus I, because you have seen this when we worked with quotient groups. And this is I itself. Okay? Now, can you tell me which element goes to 0 plus I, the identity in here? Which elements goes to the 0 of the factor ring? Now the question here, what elements that if you take the coset, you go to the 0 coset? Again, pi takes element from the ring R to R over I. For them, take an element to its coset. Now my question is, what element will go to the 0 coset? And you shall answer. So the question again, what are the elements of the ring R that has I as their coset? And you will see that means what? Let's see. Okay. So it says pi is a surjective homomorphism with kernel I. Okay. So what we want to see here, R plus I will be the same as I. So let me write in here I, which is 0 plus I, if and only if. So R plus I is the same as 0 plus I. That means R minus 0 belongs to I. Oops. But that means R belongs to I. So the kernel of pi will consist only, let me write it this way, of the elements that belongs to the ring R, such that pi of R equals the 0 of the factor ring. But this is the same set as we have written there. What is this thing equals? The image is R plus I, and what is the 0 in here? 0 plus I. Oops. But as we have above there, this means now we change that with R belongs to I. Oh, okay. So simply the kernel of pi is I. Here we go. So we got the proof for this thing. Now, what's about surjective? Here we go. Let's use this color. So this is the range of pi. The set of cosets. So, giving a coset in R over I, does it have a pre-image? Oh yes, it's a coset is represented by some element. So take the image of that element with pi and then give you back that coset. So I will leave it for you to write it. Is simple or obvious. And what's about a homomorphism? And yes, it is a homomorphism, because that depends on the definition of multiplication and addition of cosets. So I will let you write it by your own. Okay. And maybe just let me scratch it. By is homomorphism, ring homomorphism. That means I want to show that this equals pi of R1 plus pi of R2, and we have done this for groups. So let's assume for addition we have done it when we worked with the group. So let's assume for multiplication. What does that mean? So what is this? This is R1, R2 plus I. What is that? This is R plus I. Okay, what is this? This is R2 plus I. Now we are saying we want to multiply these things and get that. Oh, but this is already the definition of multiplication of coset. So pi is surjective. And so we have proved that every ideal is a kernel of some homomorphism defined and this way we will need it now for the first isomorphism theorem. First isomorphism theorems for ring. We have seen the first isomorphism theorem for groups, and this will be the same thing but adding one more operation. For groups it was only one operation, right? For rings we have two, and same thing will P as before but with adding one more operation. Let's see that's what it says. Assume F from R to S is a surjective homomorphism from rings with kernel K. So K is the kernel, okay? Then the quotient ring R over K. So fine. So we can define the quotient ring of R over the kernel. We will not be able, we could not do so unless we prove K, the kernel, is an ideal. And we have already proved that. So we can say R over K, the factor ring, is isomorphic to S. So it is the same as S. It has the same structure as S. So R over K and S, we look at them as one ring. The elements have different shapes, but the algebraic structure is the same. There's a one-to-one mapping between these two rings, which preserves the two operations. When we worked with isomorphism in the groups, the isomorphism has to preserve one operation. But now we are in a ring, so we have to preserve two operations. Okay. Now, we want to show that R over K and S are isomorphic. So we need to define a function from R over K to S. And the input is a coset, and the image is an element in S. So let me represent that in some graph what is happening here. So let's assume this is the ring R. And this is the ring S. And we have F, which is surjective. Surjective homomorphism. Okay. Now what's happening here, we will do some movement from R to R over K. And we will call that map pi, because we have already defined such one, where, let me write it here, pi was from the ring R to R over I, the very last theorem we saw, but now our ideal is K, the kernel. And it takes an element and it sends it to its coset. Good? Okay. Now what we do, phi, this map in here, is defined from here to here. This is phi. It takes R over K to S. And what does phi do? It takes an element R plus K. This is a coset, right? And R was an element in the ring. Okay. And this map in here takes R to some element in S, which is f of R. So f does that. Okay. And then this phi will take this coset to this image. Good. So what's happening? Instead of taking R, small r, by f to some place, we split this in two stages. Take the coset of R, and then take the image of that coset to be the image of small r. Why are we doing so? Because we know that R plus K here, this is the very intuitive idea of isomorphism. R plus K is a set, not only an element. R here is an element, one single element. And there are many elements inside the ring R, maybe many or some or infinitely, that have the same image as R. So if I collect them here, all of them will go to the same image as R. And you know what element are these? They are all the elements in this cassette. Exactly. So this cassette will be taken by phi to this specific element. So it is not only small r going to here, it's also the whole cassette represented by r will go to the same place, will take the same image. So what we do with the ring capital R, I wish I called this element A, so that when I say A, not saying, keep saying R, small r and big R. So I will repeat the story with this new name. So taking this element small a to its image f of a, we would like to take all elements in the ring R that goes to the same place as A. All elements of the ring R that shares the image of A. But it happens that all these elements are precisely exactly the cassette of A with respect to K, the kernel. Okay? So let me do it this way. We have a domain, and we have F going from a ring to S. From a ring to ring. I picked an element in the domain, and I know where the image is, in S. But my question in here, in this domain, I will ask for all elements in the ring R that goes with A to the same spot. And the answer is, those all elements form the cassette with respect to the kernel, the cassette of A. So cassette of the kernel will go to single element, another cassette will go to another element, another cassette will go to another element. And this is what's happening. So we splitted, we factored R with respect to the quotient ideal kernel, and then we sent each cassette to some specific element. And then we got an isomorphism. This is the whole idea. Now, so we to prove this R isomorphism, we need to show that this is now an isomorphism. I will define the homomorphism one-to-one and on-to. So we got the idea, and now let's go to the techniques. But before we start doing so, we must make sure that phi is well defined. And when we worry about a function, whether it is well defined or no, we do worry whenever the inputs are equivalence classes or cassettes that can be represented differently by different representatives. So we want to make sure that whatever representative we choose, the image of phi will stay the same thing. Now, how we do it? So I will do a sketch for the proof. If A and B gives the same cassette, and we have done this in detail when we work to the proof. So I am repeating what's happening in here. So I want now to show that f of A is the same as f of B, right? And this is what I have said before. The elements that goes to the same image, they are in one cassette. This is what I'm saying here. Now this is, if they are in one cassette, then they go to the same image. They share the same image. This is what what is the story I already told you about. So this is the question now. Can we prove this? And it is so quick. Since this is happening, then A minus B belongs to K. K is an ideal, right? But K is a kernel. So f of A minus B equals 0, the 0 of S. Okay, but f of A minus B is same as f of A minus f of B, right? Because we got a homomorphism. This and this are the same. And this equals 0. Okay. And that means f of A equals f of B. Okay, what is f of A? F of A is phi of A. Sorry. F of A is phi of the cassette of A, right? According to this definition in here. This f of A is phi of A plus K. So I need to fix what I wrote in here, sorry. And this equals phi of B plus K, and then we are done, right? And what I need to fix here is just to write phi of A plus K and phi of B plus K, because the inputs of phi are cassettes, not elements. So I need to fix that. This is phi, come on, of A plus K. Look like, okay, yes. And the same as phi of B plus K. Yes, two equals element give the same image. So it is well defined. Okay, now I want to show injective, which is like, it looks like the converse of well defined. Okay, injectives, I want to show that if a phi of A plus K equals phi of B plus K, then I want to show that these cassettes are equal. If they have the same image, then they are equal. This is what I want to show. So, but this equals f of A, and this equals, so if we have that, this is f of B, okay? And this gives, their subtraction is 0. F of A minus f of B, but f is a homomorphism. Okay, so f of A, B equals 0. And that means A minus B belongs to the kernel. Okay, but that means they give the same cassette of K. Right? And this is proved. Now phi is surjective. Clearly phi must be surjective, right? Because it takes to the image of R. So phi is surjective since f is surjective. Or literally we will write okay, let me write it in details. Phi, remember phi goes from R over K to S. So to be surjective, every element in here must has a pre-image. Okay, so if small s belongs to capital S, then there exists R belong to R such that small s equals f of R. And why is that? Because f is surjective. Okay, so what we got in here, s equals phi of this cassette. So okay, so we got an element in here, R plus K, that goes to small s, and so phi is surjective. And now phi is a homomorphism, and we have just shown that previously. So I mean phi of a plus k times, oh, let's work it out. Yeah, let's work it out. So that means phi of ab plus k, right? And that's by definition of phi, this is f of ab, correct? But f is a homomorphism, so this is f of a times f of b, correct? But f of a is phi of a plus k, and f of b is phi of b plus k. And so we have done it for multiplication. Multiplication, in here is multiplication, in here, and in here, and in here. Now same thing, very same thing, repetition. If this was addition, then we have addition in here, addition in here, addition in here, addition in here, and then phi is a homomorphism indeed. So phi is homomorphism, is one-to-one, is surjective, is well defined, and therefore finally we get R over the kernel. I would like to write it this way. I want to write it in some, I will give it a box because I want you to see that and get used to it. Now if we have f going from ring to ring, which is surjective, okay, take the domain over the kernel of f and gives you a factor ring, it will be the same as S. Okay, so take the domain and factor it by the kernel of that surjective homomorphism, and that gives you S. Okay, intuitively speaking, if we have a homomorphism from a ring to another ring, surjective homomorphism, I will reclassify this ring so that I consider all elements that goes to same image as one element in R. This I call collapse, or classifying, or factoring the ring by the kernel. The images that goes to the same image, the elements in R goes to the same image, they differ by an amount of kernel. This is a very good statement, I believe. If two elements in the domain R goes to the same image in S, that's because the two elements differ by an amount of a kernel, from a kernel, differ by an element from a kernel. That means one of them minus the other gives you an element in the kernel. The difference between them is an amount of the kernel. Once that amount goes inside F, then that amount is demolished, is collapsed. Then that amount, the difference amount, will be gone, will disappear, and then these two elements will be the same. Very interesting to look at things in algebra this way. Okay, so let's see what does the quotient ring in here looks like, and this quotient comes after the isomorphism theorem. Remember, we have a map from z of x to z. It was real numbers what we have seen. Okay, but let's take it this way, f, and define it by take a polynomial and send it to the image of 0, its image over 0. So what f will do, it has an input, a polynomial, and it gives you image of that polynomial by substituting the 0 in that polynomial. And then what is kernel f consists of all polynomials that has no constant term, right? Which means every term has an x, which means multiples of x, and I have already talked about this. Okay, And therefore now, by the first isomorphism theorem, what we get? The ring in the domain factored by the kernel is isomorphic to the image. Very interesting. The ring, polynomial rings over Z, string of polynomials, just factor them over that ideal generated by X gives you Z, gives you Z back, gives you back Z. Okay, what do the homomorphic images of ring Z look like? Oh, interesting. So if I have, and this is surjective homomorphism. So the question here is, what S looks like? What S could be? These are the homomorphic images of Z, right? Because how F is a homomorphism. Take Z to somewhere. Okay? But we know that S, the one we are asking about, is isomorphic to Z over kernel F. Good? But kernel F is an ideal of Z. It must be an ideal of Z. And we know that all ideals of Z are of the form NZ for some n integer, right? Because we know that the subgroups, ideals are subgroups, and the subgroups are of Z are of that form, and therefore we are saying if the kernel of F must be something like this. Now let's take this here and see what's happening. So it will give us that, replace the kernel by some of these ideals. So okay, so S will be isomorphic to one of these things, and therefore, and we know this, Z over NZ is isomorphic to Zn. So S will be isomorphic to Zn for some integer n. So the question, what S looks like Z sub n for some n. And how do you know that? Again, because this is simply isomorphic to Zn. So homomorphic images of Z are either Z2, Z3, Z4, Z5, or Z something, Zn for some n. Okay, and this brings to the end of this lecture. Thank you.